Well, welcome back, ladies and gentlemen. Our focus today is going to be on modern atomic theory. Now, previously, we have talked a lot about pre-modern atomic theory. So we have gotten to the point now where we know that there are protons and neutrons that are found inside of the nucleus. And we currently believe that electrons are orbiting around the outside of the nucleus in set paths. Now, what we're going to find out today is that that is not necessarily true based on what is known as the quantum model. And we'll even learn a little bit more about that in our next lesson. So it's going to get a little bit heavy. It's going to get a little bit more focused on physics, but hopefully you'll find it interesting and intriguing moving forward. So just a little bit about our learning targets for this particular video. You should be able to understand the need for a new atomic model. As more recent discoveries, we find out that the previous atomic model just simply doesn't fit. And then also be able to explain some fundamental concepts about light and how it relates to electrons and the role of this new atomic model. A couple of key vocabulary terms for you here. We're going to be focusing on the electromagnetic spectrum. We'll talk about frequency and wavelength and how that relates to the speed of light. We'll also talk about ground state electrons and excited state electrons, along with the photoelectric effect and the concept of a photon. So we need a new model. Well, why do we need that new model? The current model does not explain how electrons are distributed around the nucleus. So all we have right now are that these electrons are just in some random orbit around the nucleus, and that there are electrons that are closer to the center of the nucleus and then electrons that are further out in these set paths. Now, if electrons are negative and the nucleus is positive, shouldn't they attract? Now, if this were the quantum model, then those electrons would circle, get closer and closer and closer until eventually they actually collide with the nucleus. And we know that that is not the case. So this particular model, which is known as the Bohr model, you'll see that here in just a little bit, is not an accurate representation of what an atom should look like. So a couple things we need to keep in mind are concepts that are related to light, and light is a wave. We know this because visible light is part of the electromagnetic spectrum. You've probably seen this before in some previous science classes. Each part of the spectrum is a type of electromagnetic radiation, which is a type of energy that exhibits wave-like behavior. So as you can see on the left-hand side, we have long waves, things like radio waves and microwaves, and as we go towards the right here, the wavelength gets shorter and shorter. Now, as the wavelength gets shorter, the frequency of the wave increases. As you can see, there are more waves on the right-hand side closer to gamma than there are on the left-hand side closer to radio waves. You can also look right there in the middle and see that visible light is a part of this spectrum. You probably heard the term Roy G. Biv before: red, orange, yellow, green, blue, indigo, and violet. That indicates the order of the electromagnetic spectrum, going from the longest wavelength to the shortest wavelength. Also notice the unit that is present on those wavelengths. That is nm, which is short for nanometers. So keep in mind that light is a wave. We can see that because it's part of the electromagnetic spectrum, right there in between infrared and ultraviolet. Now keep in mind, when we talk about waves, waves are repetitive. They go up and down. The wavelength is the distance between the adjacent peaks on waves. The wavelength is the distance between peaks on adjacent waves. So you go from the one peak to the next peak in that wave and you have a wavelength. The amplitude is the distance, kind of like the halfway distance between kind of like that line right there in the middle and then all the way up to the top. Frequency is how often they occur. So as the frequency of the wave increases, as we have more waves, the wavelength actually naturally gets shorter. So for example, in this particular picture, I have 3 waves. If I had more than 3 waves in that picture, the frequency would increase because there are more waves, but the wavelength would decrease because I have to shorten the wavelength in order to get 6 waves to appear in that particular picture. So as we can see, wavelength and frequency are inversely proportional to one another, meaning that as one increases, the other one decreases. So as we see here, we have a nice little equation that frequency and wavelength are indirectly related to one another. So we have a couple of variables here. C is equal to the speed of light, which is 3 times 10 to the 8th meters per second. That is a constant. Lambda is the wavelength, and then the V here is the frequency, and that is measured in hertz. So we'll be utilizing this as a formula to be able to calculate for things like wavelength and frequency. So here's an example of a practice problem. Suppose a certain type of wave has a length of 2.19 times 10 to the 10th meters. What is the frequency of this wave? Well, we have our given and our unknown as frequency. And we know our formula, C equals lambda V. We just simply plug in the numbers from the previous part of the presentation, 3 times 10 to the 8th meters per second, is equal to 2.19 times 10 to the 10th meters multiplied by V, which is your unknown frequency. Algebraically solve, and your frequency is 0.013 hertz for Hz. Now, interestingly enough, light is also a particle. There's this concept of this thing known as the photoelectric effect, and that's the emission of electrons from a metal when exposed to a high-powered wave. So the way I like to think about this is a fork in a microwave. You put the fork in the microwave, eventually there's enough energy that's put into that microwave where it starts to spark. Now, one thing to keep in mind is that the wave must be a minimum frequency to cause the emission. So, for example, if I take a fork and I hold it next to a cell phone that does emit some form of electromagnetic radiation, that fork will never spark. That is because the cell phone does not emit enough electromagnetic radiation to cause the photoelectric effect to occur, and therefore electrons will not be emitted. But in a high-powered wave, like a microwave or gamma radiation or X-ray, we can cause particles to shoot up, little packets of light that are known as photons. All right? And because of this, we assume or we know that light must have a particle quality with it as well, as it is what's called quantized, meaning that each photon or each bit of light that is emitted from the metal has a specific amount associated with it. So we said energy exists in small packets known as a quantum, and as a particle, this is known as a photon. There's also another relationship between the amount of energy and the frequency of that wave, and that is E equals H, which is Planck's constant, and V, which again is the frequency in hertz, so E equals HV. So again, we can utilize these, you give one variable, solve for the other. Also keep in mind that frequency is in both this equation and the previous equation, so we can utilize both equations in the same type of problem. So let's take a look at some of these problems in action. What is the amount of energy released by a wave with a wavelength of 5.000 times 10 to the negative 7th, also known as 500 nanometers? Well, we know that we have a couple different equations we can look at. The first is that C is equal to lambda V, and we also have an equation where we have E is equal to HV. So the question is asking for the amount of energy. Well, the only formula that has energy in it is this, but the only thing given to us in the problem is wavelength, which is this value. So if we take a look here, we know C is the speed of light. We know lambda, we can solve for V. Then we can take this number, plug it in here because we have a value for H, and then we can solve for E. It's a little bit complex, but bear with me here. So the only thing given to us is wavelength. And again, we know the value of C. So let's plug some numbers in here. So we have 3.00 times 10 to the 8th meters per second is equal to lambda, which is our wavelength, 5.000 times 10 to the negative 7th meters. And our unknown is our frequency. Well, we can use some algebra here and actually solve for our frequency. And so what we get is 6.00 times 10 to the 14th, and our unit there is hertz because it's a measure of frequency. Now that we have this information, we can plug it into there. We know H, we can solve for E. So E is equal to Planck's constant, which, if we remember, is 6.626 times 10 to the negative 34. And we're going to multiply that by 6.00 times 10 to the 14th hertz. Okay. Now the value for this unit here, which I forgot to write down, is actually joules times seconds. So what's going to happen is that the seconds are actually going to cancel out because hertz, the actual unit for hertz is 1/seconds. And we'll get our energy in joules when we go through and calculate the answer to this problem. And so what we find is that E is equal to 3.98 times 10 to the negative 19th joules. Okay. Now again, I know that's a bit tricky here, but if we take a look, we need energy, we know wavelength, we have a constant value for C, we have wavelength, we can solve for frequency. Take that frequency, plug it into our second equation because we know H, and then we can solve for E. So it is a bit complicated, but as long as you go through, follow your numbers, think about what variables you have, you can actually go through and solve these problems fairly easily. So the very last bit of this particular video describes what's called the Bohr model. And within the Bohr model, electrons exist in specific energy states for atoms that are different for each element. So very similar to how we discussed earlier that electrons hypothetically exist in these little orbits that go around the nucleus. Now again, we know that that is not true, which you'll find out in our next video. But this idea actually still rings true today. Electrons at the lowest possible energy state are known as ground state electrons, and when an electrical current or a photon gets onto one of those electrons, it provides it with energy. And when it provides it with energy, the electrons can actually jump to an excited state, which is then further away from the nucleus. Now, when that excited state when the electron releases that energy back, the electron then goes back to the ground state, but it emits light. You may actually be very familiar with this concept, as it is how neon lights work. Electric current is passed through, which excites the electrons in the neon gas. When those electrons go back to ground state, it releases some light, which is what you see in a neon light. So just kind of keep that in mind, that there are some ground state electrons. When you add energy, they jump up to the excited state. And when they release that energy, those electrons go back to the ground state, but a little bit of light is produced. So I know it's a bit complicated to understand because we're really getting into the physics part of chemistry. But the big thing to keep in mind here is that light exhibits both wave and particle behavior, wave-particle duality. That's why we have the wave equation that's associated with it, as well as the particle equation that's associated with light. Electrons are emitted when enough energy hits a metal, and keep in mind that electrons exist in very specific and discrete energy states, as discussed by the Bohr model. So I know it's a bit tough, as I said before, but get a basic idea of what's going on here with our new atomic model, and you'll be in good shape. We'll review this when we come back to class. Also be sure to be able to explain the fundamental concepts of light and how that relates to electrons' role in our new atomic model. Next time we're going to talk a little bit about quantum theory, and we're going to continue our work in this very complex and somewhat difficult to understand unit. Hope you have a great day, guys, and we will talk to you next time. Bye-bye.